First of all, a warm welcome to you to this today's Turing Techtalk Series. Today we are going to cover the work of Professor Amir Pnueli, and the speaker today is Dr. Basant Rajan, who is CEO of Coriolis. Following the tea break, we will have the second part of today's session, which will be focused on formal verification methods by R. Venkatesh from TRDDC. To just give a brief recap in case you have not been attending the previous sessions as to why we are doing this. As you all know, last year was the centenary year of Professor Alan Turing, who is well known as the father of computer science. He is a mathematician, logician, cryptanalyst, and more interestingly, is also a long-distance runner. And he has contributed immensely to the field of computer science. And his the formal mechanisms that he has devised, or he had devised, are the basis for what we call today as algorithms and computation. The whole concept of Turing machine and other things has been some of his seminal work that he has done. And that's why he's considered as the father of computer science and artificial intelligence. And so last year, when it was his centenary year, we decided to kind of celebrate it because his contributions, though we are all students of computer science, his contributions are not necessarily well known to many of us. And thought, this would be a nice way to kind of recognize his contributions. And the way we did this was we celebrated the event through a series of monthly Tech Talk series where we focused on recipients of the Turing Award. The Turing Award is named in honor of Professor Turing and is considered to be an equivalent of the Nobel Prize in the field of computer science, and is awarded every year to very, very distinguished contributors in this domain. And so we decided to kind of really focus on all the Turing Award winners in the last 50 odd years, 60 years that it has been the awards have been handed out. And so we completed the centenary year last year, and given the audience interest and the attendance and the support that we got from everyone, we thought we would just continue this because there's a lot of interest in people who wanted to listen to contributions made by these stalwarts in the field of computer science. So the timetable for the last year's session, all the talks, previous talks, the presentations, the videos, all are available on our website. You can go to our website and take a look at it. In addition to that, the upcoming series will keep updating those with the future talks that we are planning for this year as well. So the next talk, just to remind people, is typically we have this on the last Saturday of the month. So, but next month we are going to have a slight change of program. We would have it on the third Saturday of the month instead of the final Saturday. So it will be on October 19th. And the speaker is Dr. Hemant Pandey, who will talk about the life and works of Dr. Fran Allen. So coming to today's talk, we're going to focus on the life and work of Professor Amir Pnueli, who has made seminal contributions to the field of temporal logic, as well as to program and system verification. And to articulate this concept, we have we have Dr. Basant Rajan, who is the CEO of Coriolis, to really to spend time with us to, this topic is not a very easy topic, so he'll take, I'm sure he'll make it very simple for all of us to understand the basic concepts of the program and system verification as well as the temporal logic. If you are interested in knowing who are the Turing Award recipients, you can go to the amturing.acm website, and you can see all the Turing Award lectures, the lectures that are given by the Turing Award recipients when they receive their award. And of course, like I said, our website has the presentations that we have conducted as part of this series. And if you have any suggestions or any thoughts how we can improve this program, feel free to write to us at turing100@persistent.co.in. So without further delay, let me take this opportunity to welcome Basant here. Basant, we're really very pleased to have you here. As I mentioned, Basant is the CEO of Coriolis Technologies. Basant has about more than 20 years of industry experience where he has combined both research and technology in whatever area that he has worked on. And his focus has been in many fold, focusing on storage, on parallel processing, distributed systems, real-time systems, and of course, formal languages and logic. So we're really very pleased to have you here, Basant. And just to let you know, he has a PhD from TIFR in Bombay, of course, in the area of computer science. So we can't have a better speaker today than Basant to articulate the contributions made by Professor Amir Pnueli.
So thank you for that kind introduction. I shall try my best not to butcher this man's work. What I'm going to attempt to do is introduce the areas that he worked in and hopefully set a stage for the next speaker to take you to the applications of his work. So it's going to be a little dry, bear with me. I am told that there are a couple of kids on a remote link, right? So, and they're undergrads. Okay, so let's see how much fun this can be. So let me start with Pnueli. I had real trouble trying to figure out how to say his name. So I've been Googling and found the place. It's pronounced, apparently, Pnueli. Okay, so I'll try and keep sticking to his first name, not because I know him that well, but it's easier to say. So let's get on with it. I'm going to get off on the wrong foot. I did a little bit of Googling for his images, and the guy is a Turing Award winner, and Google gave me these 3 pictures too. The middle one is Leslie Lamport. The ones on either side, I don't know who they are. Okay, if you know who they are, let me know. I'll add them to my speaker notes. For a moment, I thought the left was Amir in his younger days. But when I saw the middle one, I was very sure that wasn't Amir. And the one on the right didn't look like him either. Okay, so if you depend on Google for all your data, this might happen. So let's get on with the topic for the day. The rest of this talk is going to look something like this. We're going to spend a little bit of time on Amir the man, primarily because I don't really know much about him. It's what I've gathered from the web, so I'll put that in front of you. The rest of it is going to be introductions to logic and program verification, just as a means to introduce the area that he is famous for, temporal logic. So once temporal logic has been introduced, I will touch upon reactive systems and synchronous programming. Those are application areas where his work was quite relevant. And actually, he defined quite a few things in those pieces as well. So the man. Let's get the awards and honors out of the way. The Turing Award in 1996, the Israel Prize, the highest civilian honor in Israel, 2000, the ACM Fellow in 2007. Now, this is an aside that I don't want anybody in ACM to hear. Not quite sure what the delay from 1996 to 2007 was about. I mean, the guy got a Turing Award in 96. What does it take to get an ACM fellowship position at that point? Okay, seminal work. It's not that the guy has only one. I'm going to talk only about one. So temporal logic of programs is something that he published in 1977. And that's been the basis of pretty much all his future work. So I will talk about that in the coming slides. More about the man. I won't read through that stuff, but give you a moment for it to sink in. Interesting thing is, he dabbled in companies as well. He started 2. I'm not sure, I mean, they are all in reactive systems areas, all instance 2 of them. he died of a brain hemorrhage in 2009. And that's the guy out there. And he actually looks like that almost always. He's smiling all the time. The rest of the talk is a dummy's guide to the hard part. Okay. Logic, program verification, temporal logic, reactive systems, and synchronous programming. Let's start with logic. So I'm not going to actually say, I'm not going to go into logic a lot, but this is just an introduction to set up the space for the rest. The study of reasoning is logic. And when you talk about reasoning, there are at least 3 types that come to mind: inductive reasoning, abductive reasoning, and deductive reasoning. What is inductive reasoning? When you condemn a man to death because you have proved beyond reasonable doubt that he committed the murder, it's more or less inductive reasoning. It's probabilistic. It's beyond reasonable doubt. Okay? Abductive reasoning is the process of discovery. You start seeing a whole lot of events that seem to be correlated, and sometime along the way the Mentos moment comes along and you say, oh, that causes this. You have discovered something, a relationship or something of the kind. That's abduction. Deductive reasoning is the only kind of reasoning worth calling reasoning. That's mathematical proofs where every step of the way you know what you said. How's it there on Mars? No idea. Okay. Deductive reasoning is deterministic. There are no ifs, maybes, things like that. Or actually, there are ifs. There are if this, then that. That form of reasoning is deductive reasoning. It's deterministic. And that's pretty much the only form of reasoning that makes sense in math. Logical forms. If you're going to be talking about reasoning and how to reason, you need a way of expressing yourself. You could use natural languages. It leads to a lot of ambiguity. And you could use formal notations, a set of abstract rules that clearly specify what you're trying to say. That's what I'm going to try and introduce you to now. Let's look at the first line out there. All men are mortal. Simple enough to understand, right? I'm pretty sure most of you would conclude women would die too. Right? But the statement doesn't say that. All you could really infer from that is if a person is a man, then he shall die. That stated mathematically is what's given below that. Given there's a function called man, which takes a parameter person and tells you true or false if he is a man. And there is a function mortal, which takes a person and says, and gives you a Boolean out which says whether he would die or not. Then the statement above means for all x where man x is true, mortal x is also true. This implies, mathematically, the concise form of saying it is for all x, man x implies mortal x. The last line is the mathematical notation for all, and implies is that arrow is implies. That is normally the language in which formal logic or predicate logic is expressed. And that statement doesn't say anything about women. So when we talk logic, we got to be very specific about what we are saying. We mean only what we say, and we have to say all that we mean. Okay? You can't leave things for, again, going back to the judiciary, which I don't particularly have a fancy for, if a person cannot be proved guilty we assume he's innocent. He hasn't been proven innocent. It doesn't mean he is innocent. Okay? So specificity is necessary. So predicate logic is something that we will just try going into. There's a problem with the statements of the form. Let's say, no, I won't go there. Let's just take the next slide and I'll take it from that statement. Some candidate is preferred by every voter implies every voter likes at least one candidate. You guys understand that statement? Right? I don't think you did. Do you understand that notation now? It's a leap of faith. I showed you what that notation means in the previous slide, but I'll make things a little easier and say that statement in English means there exists a candidate C such that for every voter V, C is preferred by V. Is that what the statement on the top meant? Why? What I wrote there is exactly what I wrote on the top too. It's just that where do you put the bracket? Right? How do you associate some candidate is preferred? That some candidate that was preferred was C. Right? You could interpret the line on the top the way I've written it down there. This is another way of interpreting the first line, which is what you most of you had in mind when you read that line, which meant for every voter V, there exists a candidate C such that C is preferred by V. Okay? That was the meaning that you took from that statement made on the top. But I could rightly say that the second statement, or the third one in this case, is what I meant. Lawyers are good at doing this. So what's interesting here? If you do not have the means of saying or quantifying existentially or universally, there are some statements you cannot make. So in Aristotelian logic, you couldn't say this. You couldn't actually talk like this. So let's take this further. So what we talked about earlier was for toddlers and for kindergarten. Now we go a little further and say, what's past kindergarten? If you're talking about logical systems, you got to look at it from the point of view of the properties that logical system has. This is crazy. Okay, I can't see the notes. Okay, let me see if I can fix that. Sorry. Okay. What does consistency mean in a system? No, that's determinism. So consistency basically means no two theorems in this system contradict each other. Okay? Validity means you will never be able to prove a wrong theorem from known facts. Completeness stands for a system where, it describes a system where every true theorem can be proved. And soundness is kind of a corollary which says, if a theorem is proved, if something is proved, then it is a theorem. Okay? So this is again where normal, natural language processing and math fall apart. They go their different ways because we have a feeling that if something is proved, then the not is false in math. In human language processing, that doesn't necessarily hold. Same old example, if somebody is proven not guilty, doesn't mean he's innocent. It only means we didn't have the proof to pin him down. So when you say that only a handful of our politicians have ever gone to jail for corruption, it doesn't mean the rest are clean. It only means we can't prove it. Okay? You can't talk about logic without mentioning Gödel's incompleteness theorem, but there's a caveat I'm going to use. I guess you know what OOS stands for. How many of you are just out of college? You don't know what OOS stands for? Exactly. It's out of syllabus. We won't go there today. Okay? Once you get into the job scene, you say out of scope. You don't say out of syllabus. But either way, we ain't going there. It doesn't want to go further. What's up? Okay. Okay. So we've taken logic, put it in a small display box, we looked at it, and we hope we can use that for the rest of the talk. What we're going to do with logic is try proving the correctness of a program. Okay? Why prove the correctness of a program? How many of you are in QA teams? Quite a few. If I were able to prove the correctness of every program that your dev team did, you'd be out of a job. Right? Thankfully, I can't do it yet. So what does proving do? It deterministically shows that what the program does is what it intended to do, what it was intended to do. Testing, however good you are at it, will only say that all the test cases I tried worked. Right? It's probabilistic. The more you test, the more confident you are that the program you are testing works according to spec. But you can never really be sure. Proving takes out the non-determinism there, the probability part of it, and says, for sure, this program is correct. Now, whenever you try doing verification, there's one thing that typically the QA team will crib about. Where's the spec? The rest of you, I assume, are in development, right? Two of you said QA, the rest are in development. How many of you have written a spec? One guy. Wow. I honestly didn't expect anyone. So if you were to tell the QA team, check this one out, you need to also tell him against what? So all verification is against a spec. Okay? So how can we check this out? The standard technique of doing checking is model checking. I mean, you call them model checking. What you do is you think of your program as moving through many states. You explore every state possible. That's exhaustive testing. And figure out whether the transitions in your model, when you move from one state to another, are all safe, and the properties of all what you're expecting actually happen in that model. Right? That's model checking, can be automated, reasonably mechanical. Deductive verification involves deducing proof obligations and then using a theorem prover. You basically say that at this point this must be true. Can I show it is true? Then you basically go through inputs and see that, okay, at this point this transform, this transform, this transform, this transform, this should be true at this place. You kind of deduced your way through the program and you said that you're done. There's another way of going about it, which is called program derivation, wherein only he will have a job. The guy who said he did a specification. From the specification, you refine it and you automatically generate a program. That puts most of us out of a job. If you automatically generated the program, there are no developers. If you automatically generated the program, it is correct. There's no need to test it either. So the only guys around will be the guys who specify programs. Okay? This is job guarantee for a long time to come. Okay? Let's do one program, blow by blow. We're going to use formal methods to see how we can prove this is right. So the L1 colon stands for, this is not any real language, it's a language I made up. L1 colon means label 1 in some statement. L2 similarly. What does this program do? It reads a number n and computes a factorial. Easy enough? I've initialized a to 1, and in a while loop, so long as n is greater than 0, I'll multiply the current contents of a with n, decrement n, and go back to the loop. So if you just spend a little time on it, you'll figure out that it does factorial. Simple? Now, let me write down the assertions that are true at this point, at different points in this program. The assertions I'm going to write are 3. The input assertion is what? The factorial is not defined for n greater than, less than 0, right? So input n should be true, means n should be positive. Okay? Loop a n n 0, that's the loop invariant. I'll leave that for the next slide. The output assertion basically says a equals n0 factorial. n0 is the initial state of n, what I read at input. Okay? So that should be the outcome. Now let's see how we can use these invariants or these assertions to reason about the program. The same program on the left side. On the right, we are going to try reasoning about this. Axiomatically, n factorial is 1 if n is 0, and otherwise it's n into the factorial of n minus 1. Fair enough? That's a standard recursive definition of the factorial. With me, right? Okay. Now let's look at the verification conditions. When you transition from L1 to L2, what were the assertions looking like? Input n0 must be true. You remember we said the input assertion was input n was true. Here n is n0, so input n0 is true. Let's assume n was, say, 5. Actually, we shouldn't do 5 because the factorial is going to be a pretty large number. Okay, let's do 3. When you transition from L1 to L2, the second assertion, which was loop a n n0 should be true, right? Which means loop a is 1 now, n0 n0, n is n0, right? We just read n, so the initial value of n or the current value of n is n0. Fair? That is at the transition when I moved into the loop. Fine? When I move in the loop, one iteration of the loop is over, what happens? That loop assertion should still be true. What happens there? The loop assertion is loop a n n0 and n not equal to 0, because if n was equal to 0, I would come out, right? So the loop assertion there is loop a n n0 and n not equal to 0 implies loop a star n. In the loop, what happened? I multiplied a by n, I reduced n by 1, and n0 is n0, right? So the implication became loop a into n, n minus 1, n0. That keeps being true every time I'm in the loop. That's called the loop invariant. Okay? Now, when would I do this transition L2 to L2? When will I come back into the loop? So long as n is greater than 0, right? So long as n is greater than 0, what's happening? A is getting multiplied by n, then n minus 1, then n minus 2, then n minus 3. And it goes on until n becomes 0, right? And if it is 0, what happens? You will get out of the loop. When you get out of the loop, the transition becomes L2 to L3. And the invariant, the assertion there is this. Loop A n n0 and n equals 0. I should have put a double equal to there. Okay. Implies output A n0. That implication said was A is now n factorial. And you have shown that A will be n factorial. Right? So if you can reason about every program this way, you don't need to test it. Because you're guaranteed that those assertions hold. Now in real life, we don't do all of this. But we do something similar. I assume you pepper your code with asserts. Yes, no, maybe. You do. What does that do? You're not writing a formal loop invariant, but you're basically putting some basic checks in there to say, if this assert fails, something is already wrong. Right? I don't need to go any further, this is dead. So in a way, you are doing a similar, you're taking a similar approach. You're not being rigorous enough. What it means is, if you hit any of your asserts in the program is bad, right? But you're not sure that you got all the asserts right. That's why you have to give your stuff to the QA team to say, test it anyway. What do? They test it and very often find bugs which your assert didn't catch, right? What that means is, your invariants that you wrote out there, I mean, I shouldn't use the word invariance, your assertions that you made out there were not complete. There were ways of failing without tripping up any of the assertions you put in. Okay? So those asserts are not rigorous enough to prove your program, but they are way better than not having any asserts. They at least trip you up when there are obvious faults. Okay? So this is as detailed as I'm ever going to get in this presentation. So you can you can sigh a little there. Nothing else is going to be this hard. So there are other approaches to doing this. There are functional specifications due to a guy called McCarthy. They transform a program into a function in the mathematical sense, and then use normal math proofs. So that factorial program could have been transformed into the recursive function for a factorial, and then we could prove that the steps involved actually give you a factorial. You could otherwise use explicit semantics where you can reason about the program itself. The program is an object and you can reason about it. So, okay, I said that previous stuff was the toughest. This is probably the toughest. We're going to spend a little bit of time on this. Let's look at the last line out there. I'll just give you time to read it. It's easier if you read it than I read it out. Did you get what it meant intuitively? Now, it's okay if it's not evident. I'll try explaining that. On the left side, we'll just look at the left side of the main equation. It says eval something, right? What it is doing is, it's trying to eval a program. What is the program? The assignment statement var equals expression followed by some program, S. So I split my program into one statement, which is an assignment, followed by some other part of the program. It can be anything. I don't want to know what it is. Okay. For the purposes of this discussion, that is the program. Okay. I'm going to try and figure out what it means. What does it mean to evaluate that program? But you cannot evaluate a program in isolation. You got to evaluate a program in the context of some set of variables or the environment. So I assume that the environment is A. Okay. So I'm going to try and figure out what is the value of a program which consists of one assignment statement followed by some subprogram evaluated in the context of A. Okay. I'm going to state that what it means is it is equal to the eval of the value of the rest of the program S evaluated in an environment which is enriched by the assignment statement var equals expression. Do you get what I'm saying? There was a statement, there was an assignment followed by a program. You have to evaluate this in the context of an environment. Environment is basically state of variables, right? What is the effect of running this assignment statement? The environment changes because one assignment has been added or modified. So the effect of doing eval A colon B, I'm sorry, I shouldn't use A again. The effect of evaluating the program segment in the previous environment is equal to evaluating the rest of the program in the new environment. Okay? That's the math of it. So that bind var val expression A is expression A has a value in the context of A. Right? So that's what val expression A means. You are assigning that value to the variable var. Okay? And you're binding that to the environment A. Now you end up with an enriched environment and the rest of the program S. If you're up to it, you can really split every program you write like this. The first statement is executed in some environment. The second statement is executed in the original environment enriched by what happened in the first statement, and keep doing this. When you reach the bottom, you have your output. Okay? That's doing it with explicit semantics. And that's the background. Now we get to what Amir did. Okay? Need coffee at this time? Okay, questions. Yeah. It's iterative with the. It's looking like tail recursion. Okay. Actually, you can look at it that way. Basically, you're saying that you're taking the first part out. True. To that extent, I agree. Other questions? Either I've lost you a couple of slides ago, or I am extremely good at putting this across. Something's got to give, man. Okay. So temporal logic is logic where we talk about propositions with temporal caveats. What does that mean? If I say I'm hungry, in my case, it might be true all the time. Okay? But for most normal humans, the proposition has a truth value which changes with the time of day, right? So far, all the statements we talked about were either true or they were false, irrespective of when you evaluated them. But the real world doesn't work that way, unfortunately. You need a more powerful language to talk about the real world. Real world not full of people who are hungry all the time, right? So you need to be able to say that I'm hungry now. So if you talk about temporal logic or logic with time in it, there are two ways of going about it, saying that there is linear time and there's branching time. So intuitively, wherever it takes you, I'll leave you there. I'm not going to go define that further. Now I'm going to talk about that 1977 paper of his which laid the foundation for temporal logic in comp science. He started out with setting out the background and state of art. Then he provided a general framework for systems and programs in general. Then he talked about how specifications can be enriched and what can be done with specifications of a given kind. Then he went on to talk about general proof principles, applications to programs, sequential or concurrent, and then there's a bunch of axioms and theorems and proofs about it. So I'm going to take you all the way to, I think, the third part and leave the rest as an exercise to the viewer. I'm pretty sure you will find some excuse not to go down the third, fourth, fifth, and sixth. Okay, I don't need to give you that excuse. But if you get the time and you have the inclination, do read that paper of his. It's a beauty. It's really a beauty. So the state of the art we already went through a little. We ended up doing verification using verification using invariances, but we didn't have a means of saying eventuality. There couldn't be temporal implication. That's not where we have taken it. State of the art, when he talked about it, there was eventuality in it, but we didn't talk about that. And the basic proof methods that they were using were inductive assertion to show invariance that we did for that factorial program, and temporal reasoning to show eventuality. That we haven't given you an example of in this talk so far. So just take it that it happened in his time before him. The state of the art was pretty good to reason about sequential programs, but not really useful for concurrency. That was the context in which he put his stuff together. He started off with saying, let's come up with a unified approach that doesn't treat sequential and concurrent programs differently. Okay? So he defined a system as a tuple S, R, and S0. S, and a program then becomes a sequence of states, S0, S1, S2, whatever. And now let me just go over what S was. S, by now you figured, it's a collection of states that the program can be in. What is R? R is a relationship that holds if state I plus 1 can be reached from state I. Okay? There are n states in the system. Only some states have transitions between them. So R defines which transitions are valid. This is all you need to describe a system. Every program you write basically transforms an initial state to a final state through a set of states. If you have written demons, then there is no final state, but you keep going down a path, transitioning from one state to another. Now, the beauty comes in this part. He split the state into control and data. I'll tell you why that was beautiful. Then he split R into saying there are two functions which define R. The function called next, which, okay, this control and data, let me just explain. Look at control as a set of labels. Each statement in your program has a set of, is a labeled program, let's assume. You've done basic programming in some time. Every statement had a number, right? So that was a label. So now look at the control as a set of those labels, and data, and that set of labels is finite. The data may or may not be finite. We're not really that badly concerned about that. Now look at this, the transition R. Split that into two functions, next and transform. Next takes the state. State is control plus data, and decides what the next state would be. Now, next depends on data if your statement at label control was a conditional. If you are doing if X then that, the control would jump to the then or the else depending on what you did in the if and what you were evaluating in the if, right? So the next was dependent on the data provided the control was pointing to a conditional. Otherwise, the control is the next statement. Your IP just simply increments, right? Straightforward. The transform part took control and data and decided how data would change. Okay? That is state change that we normally talk about. You assigned a variable, remember that var equals expression piece. That is done by the T, or the transform. Now, the beauty comes from the fact that a sequential program, you figured out how it's going to be represented, set of states. A concurrent program simply uses a vector for the set of states. Each thread is in one state. Second thread, second state, third thread, third state. The vector of these three states is the state of the concurrent program. Okay? One model works across sequential and concurrent programs with no extra flourish. You took a scalar, made it a vector, and voila, you are there. Right? That was really beautiful. Now, let's go look at the second part of it. Let's go and look at specifications and their classification. What part of that? Okay, I'll take the third part, which actually is interesting. Assume I am using one variable to specify time. Okay, let me go one step behind. If I didn't talk about time at all, I could not talk about evolution. Evolution necessarily means keeping track of what happened in the past to predict what's happening in the future, right? I have to be able to talk about this time and the next time, which means I need at least one time variable. If I have one time variable, then I can handle invariances, partial correctness, clean execution, mutual exclusion, deadlock freedom. Do you think that was doable, the one variable? You're familiar with, what was the last thing, that mutual exclusion. You know what mutual exclusion is, right? What does it mean? Somebody. The critical section is not being executed by two people at the same time. There's already the mention of a time, right? If you didn't talk about time, can you talk about mutual exclusion? You simply cannot. If you want to reason about mutual exclusion, you need to introduce time somewhere. Similarly, deadlock freedom. You cannot talk about a deadlock unless you have time in it. Okay? Now, it's interesting to say that we have one time variable and there's a bunch of things we can do. What can't we do with one time variable? Hint, hint, second point. We can't talk about eventuality. We can't talk about total correctness. We can't talk about accessibility, liveness, responsiveness if you're one-handed. One variable of time, I can't talk about these things. What does eventuality mean intuitively? If something is true now, something else will be true at some point in time in the future, already 2 times, right? Liveness. If you are in some state, you will reach some state. I am now in this state, in the next time instant I will be in another state. Already needs to be 2 times. So what he ended up saying is, depending on the number of time variables I am allowed, the expressiveness of the specification changes. With no time, I cannot talk about any of these. With time, I can talk one time instance, I can talk about the first set. 2 time instances, I can talk about the second set. I can reason about them. Okay? So that was temporal logic operators as Amir Pnueli talked about them. Today, when you talk about temporal logic, you will end up seeing these operators out there. I'm not going to pain you with the formal definition of each of these. Let me just, okay. So that X is used synonymously basically means instead of using the letter N, you can use the letter X. That's all it means. So there's nothing more deep in that. So what the format of this is, there's an operator on the left and the meaning is given on the right. Okay, so today if you go read a book on temporal logic, these will be the operators you're going to see there. The meaning is intuitive in there. The mathematical use or the expression of this, 1, it's difficult to get on a slide. 2, it's very difficult to get through in one day. Okay, so this is just a flavor of the stuff. We're getting on. I'm skipping the rest of Pnueli's paper. I believe Venki is going to go look at applications, right? So as I said, the rest of the paper is left as an exercise to the interested reader. We've given you the introduction to the tools that he used. So let's come back to the talk. We're going to talk now about 2 more things: reactive or event-driven systems and synchronous programs or synchronous programming. Okay, so have you any experience with reactive systems? Okay. Okay, the interactive systems is what you're looking at there. Fine, fair enough. So what's interesting, pardon? Okay. In a reactive system, it's got a very interesting paradigm. It's an object out there that responds or reacts to an input. You don't give it an input, it's inert. It doesn't do a thing. So if you look at these graphical or X displays or things like that, when say in a browser, you click on something, it does something. You don't do anything, it does nothing, right? So reactive systems, loosely put, respond only to external events and are inert otherwise. Their transitions are atomic and instantaneous. That's not true of the website, because when you click on something, it says waiting, 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 something happens. But in a reactive system that we are going to talk about, you touch it, it reacts immediately. Okay? It's look at those two terms together, synchronous, zero delay in the way it executes things. Why are we going and harping on the zero delay piece? There is a reason for it. This is a nice way to reason about concurrency. If programs didn't take time, there would be no race condition, right? So let's define time out. No more time, no more race, right? Simple to reason about programs, especially parallel ones. Okay? So if you could define a system like that, you could easily think of that system as a finite state automaton. At any point you're in some state, depending on some input, that the edge labeled by that input will be activated. You will go to the next state. And that transition takes zero time, right? Very simple to deal with automata. You guys did it, I think, third year in college, right? NFA, DFA, conversion, all those things. Very simple. And if you could reason about every program you wrote that way, it would have been great. Now let's look at a simple thing in that context. What would be a deadlock? A state from which there is no transition out, which is not a final state, right? You have no move to make at that point. Now, to prove that your program doesn't have a deadlock, all you got to figure out is show that there is no state in the finite state automaton equivalent to your program which has no transition out of it, right? And if you do find one, what's the beauty? You know exactly how to get there, right? Your test case for repro is simple. You found a state which has no transition out, follow it backwards to your initial state, and you know what will cause that deadlock to happen. Fix it. What's a live lock? A collection of states into which you can get in, out of which you can't. You're moving, but getting nowhere. Again, if you do find that collection, you know how to get there, which means you can check somewhere along the way, break that path. You can't enter this anymore. Your program is safe. Fine? That's why we talk about reactive programs, because we can model the behavior of that program for safety properties by just looking at the finite state automaton. Okay? Now, all this we talked about in the context of sequential programs. What happens in parallel programs? That's where all this race anyway makes them diff. Okay, I'll use a phrase which my guide used a lot when I joined my grad school, and for a long while I had trouble figuring out what it meant. And I'll do the same to you. I'm not going to tell you what it means. Okay? So he said, we compile away the parallelism into the finite state automaton. He takes one finite state automaton, which is one sequential program. He takes another, and he merges these two in this compile away parallelism, that proportion. What happens is you get one big finite state automaton, which is a single finite state automaton. It's loosely put the cross product of these two. For every transition of this can do 3 transitions. You'll have very many more states in the combined automaton. It becomes humongously large, but it is still finite. It takes time to reason about it, but it can be done. And given that a computer is the one going around trying to search that finite state automaton, you don't really care how big it is. Okay? So the same model works for concurrent programs too. That's a composition of reactive systems leads to other reactive systems which are significantly larger, but are still reactive. So all the rules we talked about, properties we talked about with reactive systems hold true for the parallel composition of reactive systems. Okay? And all of this was done, or we were humoring ourselves with these reactive systems because it leads to verification, lends itself to verification. We quickly went over how you could find a deadlock, how you could find a live lock. So you could actually look for safety properties and show that your program is or isn't safe. Where do you use this? Maybe I will be stepping on his toes at that point. So if you're flying an aircraft, not flying an aircraft, you're sitting in the passenger seat of an aircraft that's being flown by somebody, be happy that there's a reactive system somewhere there that's been verified by people much better than that pilot sitting there. So in spite of that pilot, the plane will fly. Okay? That becomes possible because of work that, say, Amir Pnueli started in his 1977 paper. More about that from Venki. I guess so, yeah? So I'm not going to talk more about reactive systems. Now, if you are dealing with reactive systems, you need a programming language which lends itself to it, right? That class of programs called synchronous languages is a paradigm in which you can write programs which translate into a FSA. FSA is a finite state automaton, which models your reactive system. So you describe your reactive system in a programming language, okay? And that programming language has a bunch of properties or features that comes standard. Sound semantics taken for granted. Every statement has only one meaning, and has one meaning and one meaning only. Determinism, no more races. Remember we said no more races. So at any point we know what will happen. If you have a race condition, you're not sure. Concurrency, inbuilt, because parallel composition is compiled away. Verifiability, we talked about it. Preemption, suspension, I haven't talked about. So now let's assume that there is a reactive system which instantaneously reacts to whatever happens. This is really a toy. In the real world, things take time, right? So you need to be able to start a process which takes time, wait for it to finish, and sometimes if you're bored with the process, kill it, right? So you need you need capability to preempt a task that you started. It could be a sub-part of the program. It's the equivalent of, in Java, the exception. Trap and get out, right? That's one. Suspend is an operator that you normally don't see in, I guess, our world of programming. What it does is, it freezes execution of one arm. Is there an example for it in real life? Where would you use suspend in real life? Okay, would you like to be suspended in the lift? Yes, virtual machines, suspend. Fine. The state is preserved, execution is suspended. Okay. Now, suspended okay, I won't go there either. Suspension can have two sets of meanings. Basically, it can be something called deep suspend or shallow suspend. Some of you would have done electronics in college, right? CMOS RAMs need to be refreshed, right? So if you have RAM that you suspended and the refresh cycle stopped, there will be no more content, right? So what you want what you mean when you say I suspended, chip select was taken out, that's suspend, right? The refresh cycle continued to happen. I didn't suspend that. That suspend is shallow suspend. I suspended up to the encapsulation of the external interface. I didn't mess with the internal working of the memory chip. So there are two kinds of suspend. We don't need to go there further. Composability is the ability to be able to take one program, put a second one, put them together and say that, okay, I can handle this, the composition of A plus B. Otherwise, I had to write A cross B myself. Okay. Encapsulation, again, I want to talk in terms of small parts. And I can do that only if I can encapsulate the implementation inside, talk about the interface with the outside world, and continue with that. Examples of synchronous programs are Estrel, that was the first one. Signal, Signal and state charts, I guess, came about the same time. State charts is something that Amir Pnueli worked on directly with David Harrell. Signal was done by a guy called Ben Minister. Mestral was done by a guy called Gerard Berry. And multi-clocked Estrel was mine. So that's why it's there. Okay. So at that point, yeah, go ahead. Okay. First off, in theory comp science, there is no real time. Time becomes just an ordering of events. If A followed B, we never ask after how much time. Okay? We don't want to know. To that extent that you're saying that in real life, the computation will take time, true, it does take time. But with relation to the behavior, with relation to the behavior, we say it takes no time because what happens is the way we do it is this. We take all inputs at a given time. Let's say the equivalent of the electronics latching. We latch the inputs. After that, what happens to the inputs, we don't care, right? Now we've got our copy of the inputs. We take as much time as is necessary to compute the output, emit that output. Just so long as no further input happens between the time the last input happened and my output happened, for all practical purposes, it happened at the time the input happened. Right? There is nobody sitting there with a stop clock saying, input aane ke baad kitna time laga. Nobody is looking at it. So long as you can compute fast enough that you can put out an output before the next input comes in, you're fine. That is something we can do for the most part, right? So that's how we marry Alice in Wonderland to the real world. Okay, other questions? None. So from tomorrow, you guys are all going to do synchronous programming. Right? Well, I showed you that you don't need testing after that. You can do parallel programs without errors. Why wouldn't you use synchronous programming? Venki will tell you why. Okay, so I think you deserve coffee at this point in time. I'll leave you with what people had to say about Amir Pnueli. The first slide said that he is already gone to a better place, hopefully. And this is, David Harrell was somebody who worked with him very closely. They were in the same place for a long, long while.
YouTube video, David Harrell's expert.
Okay, okay. You might want to go search that one. Actually, my guide worked with Amir as well, quite a bit, but I never really worked with him. So that's it for the man and his work. I hope I've given you a brief introduction to the area he worked in. And I hope I didn't scare you away from reading more about his work. Okay? Thank you. Thank you for your time. That's it.